Hi everyone, this is lecture 2 for ET 350. Today we are going to cover 6 of the 7 important fundamentals that you're going to need to understand all the motors and generators and transformers we're going to cover in this course. We actually went through one of them in the last lecture. That was the definition of flux, where phi equals BA cosine theta. Where theta is the angle between the flux density and the area, right? But now we have 6 more, and that's going to be the convention that the flux density goes from the north to the south pole. The Lorentz force is something you've seen in your physics, electricity, and magnetism course. And actually, the 4 Maxwell equations are all should have been things that you've seen in your physics and electricity and magnetism class as well. And there's going to be Gauss's law 1 and 2, which is electricity and of magnetism, Ampere's law, and Faraday's law. And Faraday's law is combined with Lenz's law. So this is the 4th Maxwell equation. But these 7 things, the definition of flux, the flux density convention, north to south, Lorentz force, and these 4 Maxwell equations, if you have these 7 things down, that is what the rest of this course is based on, okay? So make sure you have those 7 things memorized, and then the rest can be derived from this. Okay, so let's begin. Flux density. So flux density, like we said before, B units of Tesla, also known as the magnetic field. You have field lines, you've seen this before, and they're created in 2 ways. And the 2 ways are either a permanent magnet, right, like your standard fridge magnet, neodymium magnet, or an electromagnet, right? And the way the permanent magnet is a little bit of black magic, right? But the idea that you have, the spin of electrons, not that they actually spin, but they behave like they spin from chemistry. And the thing that magnetic poles have, or the property, is that they have to come in pairs. You have to have a north and a south. You can't have a north by itself and a south by itself. And that's actually ties right into Gauss's law number 2 here. And this is unlike positive and negative charges, which can exist independently. And that's basically a summary of Gauss' law number 1. Okay, so the direction convention, so that's one of the 7, is that the arrows start from the north and travel to the south. So if you had a permanent magnet, then the magnetic flux density lines leave the North Pole and travel to the South Pole, right? They leave the North Pole and travel to the South Pole. So that means for something like the Earth, if we have the magnetic field lines pointing towards the North Pole, isn't that opposite? Well, yes, it is. The geographic North Pole is actually the magnetic South Pole, if you didn't know that already, right? Because the magnetic field lines emanate from the geographic South Pole and go to the geographic North Pole, but really this is the magnetic North Pole and or down here, and you have the magnetic South Pole up here. Kind of interesting. Okay, let's keep going. All right, so this is the Lorentz force, and I have these 3D printed cubes. Okay, hopefully I can somehow get these to you, but this is on one corner current, force, and flux density. On the other corner here, you have X, Y, Z, just the right-handed basis, right? And so this cube is representative of this law, and we call it Bill's law. Now, only in this class will anyone know that you mean this law when you say Bill's law, right? So outside of this class, to the public, to YouTube, the Lorentz force, that's the proper name for it. So you can call it Bill's law in this class, but let's refer to it as Lorentz force outside of this class. So no one comes to me and goes, Chang-Siu, what is, I talked about Bill's law. No one knows what I'm talking about. Well, it's because this is the proper term. Okay, so this is F equals BIL. And now I don't have the L on the cube just to kind of make it simple, but let's break this down. So let's imagine you have a wire, okay? So you have some wire and you have some current in it, right? So wire of length L with some current, and the current is sitting and it's exposed to some flux density, okay? We're also gonna assume that this wire and this flux density are perpendicular to each other in this situation. if that's the case, the force on that wire is equal to BIL. Notice everything is a vector here, right? And the direction of this force obeys this right-hand rule. Okay, so let's say we have, here's the situation drawn out. Okay, so if I have a wire, so here's your wire here, okay? And in this wire, I have current, and this current is flowing kind of into the page. And I have two magnets. I have a north side of a magnet here, a south side, and in between, you're going to have a flux density vector going from north to south, as we just stated before in this convention. We can use this right-hand rule, ILBF, right? IBF, F, F, IBF. Okay, so let's see if this matches the cue. I, good. B, so I, B, F. Good. So I'm going to put I here. B is going into the page and F is going up. IDF. Get this memorized. Now this cube, if I can get it to you, will hopefully help you on homeworks and tests, but very useful little tool. If not, just use your 3 fingers. And use your right hand, not your left hand, please. This is the right hand rule. Okay. So let's follow the same thing here. IBF, you can see I drawn it. IBF, IBF. What does that mean? If I had some wire and I was able to run current going this way, how would I run current? Well, maybe I take a battery, I put the positive terminal here and the negative terminal here, and current's going to flow this way. And I have an external magnet, right, with the south on the side of north and the magnetic field going left to right. This wire is going to feel a force and it's going to pull it down. Kind of cool, right? That's kind of fundamental how motors work, right? You have magnets, you have wires, you apply current, things move. You get forces and torques, right? Okay, so make sure you understand the physical situation that is associated with this equation, right? It's an external flux density, and this is a wire with current running through it, and these two things are perpendicular. If they're not perpendicular, we have to use a more general formula, all right? Okay. So this is I had another slide where this is just a blown up version of this, but this F again is called the Lorentz force, right? Okay, F again, F and B going left to right, force down. Okay. Now let's check the units, because I always do think it's good to confirm units. So we have F equals BIL. And we know what L is. L is meters, it's a length. I is amps, B is Teslas, and F is newtons. So the question might be, well, is a Tesla amp meter the same as a newton, right? Is a Tesla amp meter the same as a newton? And so a newton is a kilogram meter per second squared. Why? Because F equals MA, right? We know this is true from dynamics. So we know a newton is a kilogram meter per second squared. This is acceleration kilogram. So that's one check, okay. Does a Tesla amp meter equal a kilogram meter per second squared? If that's true, then it must also equal newton, all right? So what do we have here? So we have an amp, we know is the flow of charge, positive charge, so it's a coulomb per second, and we know a Tesla is a Weber per meter squared. That's the definition of flux, right? What else do we know? I had mentioned in the last lecture that a Weber is the same as a volt second, right? And so we're actually going to use that fact. The Weber is a volt second, okay? And we might see that there's starting to get some cancellation here. Meters, right? Maybe seconds. And if you recall, a volt is a joule per coulomb, right? Energy per charge, right? So volt is a joule per coulomb, and a joule is actually a Newton meter. It's the same unit as torque. So we can start crunching and just picking away at this, right? The seconds cancel, the coulombs cancel, one of the meters cancels. And so we ended up with a Newton meter per meter, and lo and behold, the meters cancel, we're left with a Newton, yay, right? So this is all consistent physically, right? This is just something that you want to do maybe once or twice just to confirm if you see a new equation, do the units at least cancel? Does everything make sense? Is it all consistent? Okay, now is this something that you might have to do in your career? I don't know, maybe not, but I think it's just a good thing to be able to do so that you're confident with the equations that are presented to you, right? Okay. So let's look at a very simple example using this Bill's law equation, right? So let's say we have a situation where we have current. Remember, we have a wire with a dot, like an arrow. If the dots, if you're seeing the dot, means the current's coming to you out of the page. If you see like an X, it's like the arrow feathers, means the current's going into the page. All right. So in this case, the current's going out of the page. B is going left. We have a situation where B and then IL are perpendicular to each other. So that means we could use the Lorentz force or the Bill's law equation. And the question is, what direction will the force acting on the wire be? All right. Okay, so good. B and I are perpendicular. We can answer that first question using our cube. So we take I. Okay, I is pointing up, out towards us, and B is pointing to the left. So I have I this way, B, and I have force up. Force is going down. Okay, so I think the force is going to go down. I can use my right hand. I, B, F. So I is coming towards us, B is going left, F is going down. Yep, that's consistent with the cube. Excellent. So that should be going down. Okay. The other question is, what is the length of wire exposed to the B field if I is 10 amps, D is 3 Teslas, F is 30? So we can write the Bill's law. Well, it looks like I have a solution here. Yep, F is down, good. But we can look at the Bill's law, F equals BIL, good. And we can start punching the numbers, 30 for F, 3 for the magnitude of the flux density, 10 for the current, solve for L, looks like 1 meter. Okay, so this is a pretty big magnetic field, big in that it's there's a big area where we're exposing this to, because 1 meter is actually a pretty long distance to have a constant 3 Teslas. And actually 3 Teslas is actually a big number. It's just a toy problem. But when I see these numbers, wow, this is quite a bit of current and flux density, right? Okay, good. Now, you might be asking the question, is it always the case that IL and B are perpendicular? What if there's a situation where they're not perfectly perpendicular, right? What if you had the current kind of off to the side or like something like this, right? And that always happens, right? Okay, so now we can use a more formal, or I should say more general equation. It's still the Lorentz force. So the Bill's law is actually a special case of this Lorentz force equation, right? And it's F equals Q velocity cross speed. This is a cross product. We saw a dot product in the last lecture, right? Remember, the dot product is if you have 2 vectors, V1 and V2, and you dot them, then you get V1 magnitude, V2 magnitude, cosine of the angle in between. This is the dot product. Well, the cross product, this cross product is going to be, it's going to have the magnitude, and you're going to have essentially a sine theta, but it's also going to have essentially a vector associated, and we're going to use the right-hand rule, okay? And so this new vector for this one is going to look at the velocity of a charge. So you're going to have some charge here, Q, okay? So we'll say a positive charge. It's going to go in some, we'll call this the velocity vector. And you'll have some B vector here like this, okay? And then you can use your right-hand rule, V cross B, that'll be your F direction, right? So some moving charge is going to be moving like this, and if it's exposed to some magnetic field pushing flux density this way, it's going to produce a force in this direction that's perpendicular to both these vectors, right? Okay. Now, does it have the same units? Well, the original one, F equals BIL, we had already done it, TAM, right? Okay. Now we have a Tesla Coulomb per second meter. Does this Q velocity cross B also have these same units as this? Because we already showed that this has units of newtons. Well, what do you have? Coulombs, meters per second, Teslas. Do these match? They sure do. So yes, physically the units match for the original one, which we know matches newtons. All right, let's keep going here. All right, so yes, this is where I've written out the cross product, right? To fill this out, right? We had a sine theta, and you can see that here. So we have V1, V2 magnitude sine theta, right? That's the magnitude, but a cross product has a vector component, a vector answer result for it, whereas a dot product is just a scalar, right? So this is a scalar, but for a cross product, you actually have a vector. And this is the magnitude, and the direction is actually what I just said. V3 is perpendicular to both V1 and V2 by the right-hand rule, and we had already explained that, right? Okay, and then here's just another picture, a more formal picture of what's going on. If I had V1, V2, what I can do is I can take my fingers in the direction of V1 and then curl it towards V2, and my thumb points in V3. If I had V2 cross V1, then I would point the direction of my fingers in V2, go to V1, and then my thumb points down, right? So the order of a cross product matters. V1 cross V2 is not the same as V2 cross V1. You have to be careful of that. But that's something you should have seen in calculus. If not, you guys Google, YouTube, cross product, and it'll explain everything, right? But this is the math behind that, okay? All right. Let's use this cross product idea and fill in what this looks like, right? So if I have the cross product, the magnitude of the force is Q, the amount of charge that's moving, times the magnitude of the velocity, times the magnitude of the flux density, times the sine of the angle in between the magnetic field and the velocity, right? It's the angle between the velocity and magnitude. Now, if velocity and B are aligned, if they're aligned, then what happens? The theta here is 0. If the theta here is 0, sine of 0 is 0, right? Because sine looks like, let me get a new piece of paper. Actually, I can just rotate this around. Sine of theta looks like this. Here's your theta. So sine of 0 is 0. Okay, there we go. And if sine of 0 is 0, that means you get no force. So if you have a charge, there's a little positive charge, and that's moving, and your flux density is in the same direction as the charge or in the opposite direction, doesn't matter, I'm going to get a 0 for that theta, and that means I'm going to get a 0 force. The more perpendicular, or the closest this theta is to 90, or the more perpendicular this velocity is to B, the larger that force is going to be, okay? And so I have that written here. If velocity and B are perpendicular, theta is 90, sine of 90 is 1, that's over here, and the force is maximized, right? So this is the situation where we had that original simplified Gauss law in this case, right? But this is the more general version where it counts for anything in between, okay? All right, here's an example of a particle accelerator. A lot of big research labs, or not a lot of big, there are research labs that are very big that have these particle accelerators to study the interaction of protons, electrons, and all these stuff, and they smash things together. And so what you get is these huge, huge buildings. And what they try to do is get these electrons to spin around and around and around, right? And what they can do is they can apply this in a magnetic field, either up or down, to get this electron to have this force that pulls it in to keep it on the circular motion, so they can build up speed and smash it into other things, or have it spin off and go and do experiments on that. So we want this electron, let's say, to curve around. And so the question is, should we get the B, should we have a B that goes in or out of the page, right? Now, if you recall from E250 a year ago when we took circuits, this is a negatively charged particle. It's an electron, right? But this is applying to a positively charged particle, right? Okay. And so this is equivalent to a positive charge going around counterclockwise, right? An electron going clockwise is the same as a positive charge going counterclockwise, all right? So let's analyze this system using this equation, right? So if we want this force to go in, right, then we could guess, should we have a Q velocity going this way, cross B going into the page to get this F? Well, let's try it. So let's say I'm here at this instantaneous point in time, okay? At this instant, it looks like my Q velocity is going to the left and my B is going down. So Q, B, F. Yay, that looks like that force is going to do what we want, right? So that seems like a good guess, right? And if we went and applied that over and over and over, let's say we were here, so now the velocity of Q is going to the right, we could say, is QB going F going up? Yes. So at the bottom here, you would get an F. So at any point around the circle, you would get a force that's pointing towards the center of the circle. Okay. So in this case, this big scientific research lab would have generate a magnetic field that is going down from the ceiling down to the ground to get this electron to keep spinning clockwise, right? Or an equivalent positive charge to go counterclockwise, right? Okay, good. Okay, let's keep moving along. So what do we have? We have the definition of flux, we have the Lorentz force, and now we're going to talk about the 4 Maxwell equations. Good. So the first Maxwell's equation is Gauss's law of electricity. Okay, the electric flux out of any closed surface or volume is proportional to the total charge enclosed within. Oh, it's a mouthful. All right. Let's slowly parse out what this paragraph says. The electric flux. So that's like magnetic flux. Okay, fine. Electric flux, magnetic flux out of any volume, right, is proportional. So any volume, so that's like a surface, right? So we have an enclosed surface, right? So like a ball, like a balloon. So we have a balloon, right? And it's proportional. So the flux that this net has caught. So we have this net and we completely closed it, right? And the amount of flux that's cutting through this net is proportional to how much charge, whether it's positive or negative, that we've captured, right? So if I've captured more charge, I'm going to get more flux piercing the surface, all right? If I've captured negative flux, I guess it's going to pierce it in a negative fashion. If I've captured positive flux, it's going to pierce it in a positive fashion, right? And so Q is proportional to the phi of the electric flux, right? What this is stating in a nutshell is that you can capture charge. Positive and negative charges can exist independently. That's kind of the byproduct of what this is saying. This is like a very general way of saying this, all right? Okay, so that is a summary of Gauss' law for electricity, all right? Okay, Gauss's law of magnetism is a similar statement, but it says the total magnetic flux out of any closed surface or volume is 0. Huh. Here, it was like the flux is proportional to charge, but here it's saying the flux is 0 for any closed surface, all right? And the consequence of here is that there's no magnetic monopoles, all right? Let's try to visualize what's going on. Let's say we had a magnet, all right? So if we had a magnet, I don't have a magnet handy, but let's say I just had a magnet. I don't know, we'll call this a magnet. You have a north and south pole, right? Okay. If I had a magnet, and I could enclose a volume around it, am I going to get flux cutting through this? I sure am, right? Think about it. I have north coming out. I'll even draw it. If I had a magnet, north and south, these are the flux lines, right? Oops, flux lines can't cross. Okay, so like this. And let's say I took a bubble and I just kind of closed it off. Well, I definitely see flux lines cutting this, so I'm getting a phi and a phi here. But what it's saying is that the total flux is 0. That means this flux that's leaving is equal to this flux that's entering. So the net flux is 0, right? The other one is if I try to chop this in half, what happens? I get a north-south and I get a north-south. And I get the same issue, right? So let's say I go here, the amount of flux leaving is the same as the amount of flux entering. Let's say I put a bubble here. The amount of flux leaving is the same as the amount of flux entering. Darn it. What if I just did a random bubble over here? It's the same thing. The amount of flux entering equals the amount of flux leaving. I cannot just capture a north pole, a north magnetic pole by itself. I can't capture a south magnetic pole by itself. I always have to have pairs. That's what it's saying. No magnetic monopoles. Whereas here, I can actually, in this case, if I had some Q positive, If I put a bubble around it, what's emanating out is electric flux. And the more charge that's being caught, the more flux is going to pierce my little bubble, right? So this is similar, but saying a different thing than the magnetic version, okay? That's kind of it for the first two Gauss laws. Okay, Ampere's law. You've seen this before. This has another right-hand rule, all right? Okay, so we're going to have, I think, 3 right-hand rules that are going to go on. We're going to have the Lorentz Force right-hand rule, and then there's 2 versions of the Ampere's law right-hand rules, okay? Okay, what is the Ampere's law saying? It's saying the electric current and changes in electric fields are proportional to the magnetic field circulating about the area they pierce. Oh gosh, that's kind of crazy, right? So let's say, okay, so let's say we have an area, right? We have an area. So the electric currents and changes in electric fields, okay? So let's say we have an electric current and a changing dEdt, change in electric field, okay? And they're piercing this area, okay? So like you had a wire going through here, or you had like 2 capacitor plates, and these capacitor plates were oscillating in their charge, and dEdt is changing, right? If you do this and you have this area, then you'll get circulating magnetic fields, whether either by current or by dEdt. That's what this sentence is saying. That's what Ampere's law is saying, okay? Here's the kind of crazy formal general equation for Ampere's law. B dot ds equals mu I enclosed plus 1 over some constant dEdt dA. Oh my gosh, this is a lot, right? We're going to ignore this dEdt part. However, this is fundamentally how capacitors are able to allow current to flow, right? You get kind of a dEdt, and then that relates in an I, because that's kind of a weird thing. How do you have 2 parallel plates that don't touch that allow current to flow? Well, if you get a dEdt, you get some magnetic field spinning, and then you get these currents that are going through, which is kind of crazy, all from Ampere's law, right? Ampere's law is essentially kind of like a KCL, Kirchhoff's current law, right? It's like sum of the currents and nodes equals 0. It's like a current balance, right? But what this is saying is, if I have currents going this way through the surface, I'm going to get magnetic fields that circulate. That's really what I want you to take away from this, right? I know I'm giving you the full, you know, the big picture, right? But don't get lost in all the little details, right? Okay. Let's now go into how you guys are going to use this in a more simplified manner, right? I know this is a little bit confusing. Don't get lost in this. Just memorize the next page here. Okay, so we're going to have an Ampere's law, second right-hand rule part A. I'm saying the first one is going to be the Lorentz force. Now, like I said, this is only for this class, like Bill's law, only for this class. People will know what Ampere's law is, but if you say it's the second right-hand rule, they're not going to know what you're talking about, right? Ampere's law, the right-hand rule is, imagine you have a current, right, with a wire with current. If you have a wire with current, just DC current, it'll generate a DC flux density. If it's AC, it'll be an AC flux density, right? Okay, and you can use your thumb, point in the direction of current, and your fingers are showing the direction of the magnetic field that is circulating around that wire, okay? The closer you are to that wire, the stronger the flux density. The farther you are away from that wire, the weaker the flux density, okay? All right. Now, let's say you had a solenoid, okay? You had a solenoid. I'm going to call this the second right-hand rule, or Ampere's law right-hand rule part B, okay? Now, let's say you have this wire. This time, it's curling around the current, and you're going to take your fingers and put them in the direction of current, and your thumb is going to be the direction of flux density, or phi, okay? Notice the difference here. This is for a wire where the thumb is the current and the fingers are flux density. Here's for a solenoid, whereas the thumb is flux density and the fingers are current. Be very careful about the differences. You should have seen this in physics, but we're seeing it again. This is for a wire, this is for a coil. Okay. Now the question might be asked, well, is this from this? It sure is. Yes, it is. Okay. So let's look at what's going on. let's say we have our coil. This is the same thing as this. Let's just look at one cutaway ring, right? If you're looking at the top, see how flux density is coming up or out of the page, and you see how the current is going, let's say, counterclockwise, right? Let's look at any moment here. If I'm looking over here and I use the first right-hand rule, can you see how current flux density is going to go down on this side and up here? If I go over here, down and up, down and up, down and up. So that means everywhere inside this loop, the overall flux density is going up. Everywhere outside this loop, the flux density is going down. If I were to stack this loop on top of others, inside here, all these loops are generating flux density that is going up. Okay, if that makes sense. And that's why the overall behavior is looking like this one, right? So this is not quite a proof of the second rule. It's, it's like a visual, I don't know, justification of why this one is actually supporting this one, okay? All right, good. Okay, the last of the Maxwell's equations is Faraday's law. And this is also fundamental KVL, Kirchhoff's voltage law, believe it or not. All right, so KVL is combined with Lenz's law. All right, so what does Faraday's law say? The voltage accumulated around a closed circuit is proportional to the time rate of change of the magnetic flux it encloses. And Lenz's law says the voltage opposes the flux change. And this is the equation that you want to have in your head. V induced equals negative N d phi dt. So if I have a d phi dt, so if I look at this, the voltage accumulated around a closed circuit, that's the voltage induced, is proportional or equal to this, right? To the time rate of change of the flux it encloses. This is the d phi dt time rate of change of flux, and this negative corresponds to the opposition, right? N is for the number of coils. So if I had more number of coils, then I'm going to have more voltage induced. All right. One thing that I want you to note in this is the d phi dt. And remember the definition of flux, B equals BA cosine of theta. Well, what would I have to do to get a d phi dt? What could change? I could change B, get a dB dt, a dA dt, or a d theta dt. D theta dt. And so in other words, you can imagine already that I can generate more voltage if I have something spinning, if I have an area increasing or decreasing, or if I have a magnetic flux changing, right? That's why I bring up the definition of flux, because it's going to intimately tie into this d phi dt term, which is going to intimately tie into the voltage induced by generators. This is how we turn on the lights, ladies and gentlemen, right? Think of the big power plants that you see, the big hydro dams, all those big power generation stations. What they are doing is applying Faraday's law and having essentially magnetic field spinning next to coils and creating a d phi dt. With that d phi dt, they are inducing voltage and current into wires that powers our lights, that gives electricity, that I can give you this YouTube video. It is amazing what Faraday's law has done for our society, right? So the Maxwell equations, Faraday's law, all this stuff, fantastic. Okay, let me give you, before we end, let me give you a small example of Faraday's law. I mean, we will be hitting, I know this is a shotgun to the face of information, right? And we will be going over and over these 7 rules, right? But let me give you a small example of how Faraday's law can kind of work in practice, right? Okay, so let's look at this simple example. You guys have seen those flashlights where you have the magnet drop in and you have a coil and then you have like a light? Well, let's kind of look at how those work. And it, again, applies Faraday's law. So let's say you have a coil of magnet wire that's wrapped around and then attached to a resistor here, okay? This resistor could be a light, right? And so let's say we're measuring the voltage induced. So I have my red lead here, my black lead here, okay? And let's say I have a magnet and I have it oriented in this fashion, north and south, and it's falling in. We know from our very first slide here is that the flux density is leaving the north and going to the south. So for all intents and purposes, the coil sees the flux density going to the left. And let's say this magnet is moving to the left, okay? From the perspective of the coil, the flux density is getting bigger because the velocity is moving to the left, right? This flux density is appearing bigger, right? Now, according to Lenz's law, Faraday's law, there's an opposition here. Now, I'm going to be a little bit loose on this sign, unless we go into the crazy kind of strict definition with all the nasty integral stuff. This is going to be kind of hard to take into account. But I want you to always think of Lenz's law and Faraday's law as there's an opposition. So if you have a B field going to the left, and you want something to fight it, there's going to be a opposing B field set up in this coil to fight this B field that's getting larger, okay? Now, this B field that's getting larger is supported by current in here in this coil, induced current, and that follows Ampere's law, okay? So Ampere's law would say, if I wanted to create this B field from current, I would need to induce current in this direction. And you can see it. You see how this current here is supporting this B opposed, okay? So this induced current, due to Ampere's right-hand rule, would be opposed. So this B induced becomes a positive voltage. Remember, current is the flow of positive charge. So you're going to build a positive charge here, right? So that means if I were monitoring this and I had my red and black lead, I would see at this instantaneous moment of time, I have a magnet like this and I'm moving to the left, I would see a positive number on my oscilloscope or multimeter at that brief instant in time, okay? It's not going to be constant, but at least it's going to be positive at this moment. Now, let's say we had a similar situation, right? Now, this is going to be very similar to the homework that you got to do, right? Let's say we had a very, very similar situation. Same coil of wire, same resistor, and same polarity in which I'm measuring. I have the same orientation of the magnet. The only difference is I'm now starting here, but I'm moving the magnet to the right. I'm moving it away. Let's see what changes. Still, my flux density is pointing right to left because the north here is, it's going this way and kind of going around, okay? But this time, the biggest difference is that this B is actually getting smaller, where in this initial situation, the B is getting larger, right? And so this coil, this Faraday's law and the Lenz's law and this coil is going to be like, well, wait, you're leaving? Why don't you stay a little longer? And so it sets up a B opposed actually in the opposite direction, right? Of the change, not of the B field. That's an important distinction. The B opposed, notice the B is both in the same direction. B opposed is always fighting the change, right? It's not fighting B, it's fighting the change in B, okay? So here it's now pointed right to left, this B opposed. And again, by Ampere's law, to support that B opposed, now that flips, and so the current now goes the other way. And now you build up positive charge on this side. And if I were to take my measurement, plus and minus here, I would actually read a negative number because positive charge is now building on my black lead for my measurement. And I would get a negative V induced, whereas here I would measure a positive V induced, okay? All right, a lot of information. Rewatch the video if any of this didn't make sense, and we will go over a lot of details in class. I hope this helps a lot, and I hope you have a great day. All right, see you later.